That is crazy. So most of the cells you're made of, every 4 months, are completely turned over.
Water rushes out of the cell, causing spike-like protrusions to form as the cell collapses.
That's awesome. So our happy little cell, if you put them in salt water, turns into an angry little cell that looks like a pine cone. Somebody in the room just farted, and the fart molecules were spreading out through the whole room. Then he talked about how the molecules were probably going in somebody's nose and hitting their tongue. And you had me at fart.
Redeem Academy.
Hey, what is up, Science Squirrels? Johnny here with Redeem Academy. I'm here to help you get the most out of your education while giving God the glory he deserves. Today is the 7th day of our cells unit, and today is all about osmosis. Maybe you've been lucky enough to watch the movie Osmosis Jones. That movie really has nothing to do with osmosis.
Go! You see this badge?
I'll be telling you about 3 things today. What animal cells do in pure water and salt water, what plant cells do in pure water and salt water, and why they change the way they do in those different solutions. Big question today, how does the truth that cells become filled with whatever they are close to relate to our spiritual lives? Ooh, so spiritual today. All right, we're gonna start off today with a challenge.
Oh yeah, brother, I'm in.
Can you explain in one word, what is going on in this video? Why this happens the way it does? Here we go. Put it in the comments if you know what it is. Now that is food coloring. Homeboy drops food coloring into 3 different glasses of water. One says cold, one says warm, one says hot. And we see it in each one. He puts in a second drop in. We see it in each one doing its thing a little differently. All right, so in one word, this one, the whole thing turned pretty much the same color blue. In this one, it's got kind of like, I don't know, lines, but the lines are kind of throughout the whole glass. And in this one, the cold one, the lines stayed more in the middle. Put a comment in before I tell you my one word for this. Why did it do that? All right, the answer, the movement of molecules from high concentration to low concentration is called diffusion. All right, now this might be the moment I remember loving science for the first time. Sitting in 9th grade biology, my biology teacher talked about how somebody in the room just farted and the fart molecules were spreading out through the whole room, and I was like an immature teenage boy, and I was like,
oh my gosh, fart has molecules. Ah!
Then he talked about how the molecules were probably going in somebody's nose and hitting their tongue, and you had me at fart. Let's not talk about farts today. My kids make fun of me because I talk about farts. When this guy took the food coloring particles were in extremely high concentration when he dropped them into the glass. But as they got a chance to spread out, they went into lower and lower concentration. And when somebody farts, I'll never stop talking about farts. When somebody farts, the particles, they come out. And they're in extremely high concentration, but they spread out everywhere into lower concentration to where there's so few of them, you can't even smell them, but they're still there. Now, what's even more interesting is that if you drop food coloring into hot water, it spreads out the fastest. Warm water, it spreads out slower. Cold water, it spreads out the slowest. So in one word, this is called diffusion. Now, if you throw in a membrane and you have water diffusing across a membrane that only lets some things go across, we call that osmosis. So the diffusion of water across a semi-permeable membrane, like a cell membrane, is called osmosis. Now, I have a great video to show you a membrane in real life. Okay, so when you get my notebooks and my workbooks, you also get some other activities in there, and one of them is this. You take an egg and you put some vinegar in with the egg, and you'll start to get these bubbles. And this is like something you can do at home. You don't have to use a beaker. Vinegar is acetic acid, so they say acetic acid in there, but really it's just vinegar. And the shell of the egg is calcium carbonate, and it makes calcium acetate. These are all the chemical names, but it smells. I hate the smell of vinegar so much. And but you leave it for like 3 days, and then all of the calcium carbonate that's on the egg will dissolve, and you'll be left with an egg. Spoiler alert, by the way, if you haven't done this yet, maybe ignore this part of the video and go do this lab that comes with my curriculum. This is like the best thing, okay? And the egg is just left inside of its membrane without its shell. And oh my gosh, just playing with one of these eggs, be careful when they pop. It's so much fun, so much fun. But that is a membrane right there around the egg. It's just one giant membrane. And you can squish it and squeeze it, and then there's some other experiments I tell you to do with it once you do this in my curriculum. But this homeboy, he just pops it, and then there's the egg on the ground, but look what's left in his hand. Membrane, okay? And that is just like a giant cell membrane, okay? And so I have some experiments that go with this, that really go with this lesson that you really need to do. If you haven't already done it. Okay, so today what we're going to be talking about is osmosis in cells, and we're going to start with osmosis in animal cells. So I'm going to write osmosis in animal cells. We are going to assume, and this is not completely right, but for our purposes this is going to work great. We're going to assume that every animal cell is 2%. So I'm going to use red blood cells as my example, and so here's my perfectly circular red blood cell. That's actually really good.
This should be in a museum.
And I'm going to assume that every cell is 2% salt and 98% water, okay? And so here's my happy little red blood cell. I'm going to give him some eyes and a smiley face. And I'm going to color him red. All right, so here's my happy little red blood cell. Okay, so here's some real red blood cells floating around under a slide. And so you can see that's what red blood cells really look like. They really are red, and they to me, look like little rafts floating in the lazy river at a water park. That's magnified 1,000 times, okay? That's a white blood cell right in the middle there, and then a whole bunch of red blood cells. So you have in your blood, you have some white blood cells, but your blood is mostly red blood cells. Okay, time for a nerdy ChatGPT search. You can vary how many red blood cells you have based on how much you exercise, but I want to say the red blood cell is the most abundant cell in the body. Let's look this up. Okay, yeah. So on average, an adult human has about 20 to 30 trillion red blood cells in their body at a time. Okay, a couple more interesting facts about red blood, because how many do we have total? I think we only have like 40 trillion cells total. How many cells total does a person have? Yeah, so the most commonly cited modern estimate is 37 trillion cells in an adult body. Roughly 60 to 80% of your human cells are red blood cells. Notice he's saying human cells because there's also a ton of bacterial cells all over our body. One other cool fact is that your red blood cells, I want to say all of your red blood cells recycle every 3 months. How often before all of my red blood cells are completely recycled? About every 4 months, every 120 days, your entire red blood cell supply has been basically recycled. That is crazy. So most of the cells you're made of, every 4 months, are completely turned over. And these happy little guys that look like little inner tubes that float through the lazy river called your circulatory system. Okay, so if we drop him into a solution of water that is 98% water, 2% salt, water is going to go back and forth in equal amounts. So I'm going to put an arrow with water going in, and I'm going to put an arrow with water coming out, and they're equal. Okay? Now, the reason water can get in is because of a special channel or tunnel protein that I haven't told you about yet. His name, these special open doors that let water in, he's called aquaporin. All right, so we're picking up in the middle of this animation. I don't know what half of this video is about, but that's a cell right there. They've kind of like cut it in half. You can see the nucleus, you can see a mitochondria and some other things. And you see water needs to get into the cell.
So let's take a look at that.
So now we're zooming in on just a piece of the cell membrane. You can see the lipid bilayer. You can see there's some other stuff in the lipid bilayer. They show you some phospholipids, that they have a head that likes water, and they've got legs that hate water. And so water can't get through. So they show you, look, water can't get through because these molecules, the top like water, but the bottom don't like water. So water's not going to go through the phospholipid bilayer. And so this is a real problem. How do you get water to go into a cell if there's like a force field and water, see one water molecule goes down, it comes right back out because that middle portion hates water. And so that's what they're showing you in this video. And every once in a while, one water molecule might slip through, but it doesn't really happen. And so they're showing you this teal molecule called aquaporin.
The cell membrane has protein channels called aquaporins. Aquaporins allow the rapid movement of water into or out of the cell. So each cell is actually full of tiny molecular holes. Aquaporins are almost always open.
So isn't that interesting? It's a little tunnel, and the cell can close the tunnel. And I mean, just think of the word aquaporin. It's a pore, it's a hole that can let aqua is another word for water, through. So it's a pore for aqua. And we see the water molecules going through.
The number of aquaporins in the cell membrane is dynamic. Chemical signals like...
And they're telling you like other things can cause there to be more of them in the cell membrane.
Increase or decrease the number of aquaporins.
So you can see a couple more of these. These are they're made out of
Like
protein.
other protein channels, aquaporins are specific.
There's a caffeine molecule, I think, is what they're showing you there. That kind of looks like sugar, maybe. I don't know.
Aquaporins are specific to water. They don't
That's a
allow
sugar molecule.
solids
The other one
out
was caffeine.
inside or
That
outside
purple
the
thing is
cell.
an ion. I'm just going to mute this guy. So you can see the ion can't get through aquaporin. The sugar can't get through. And so only water can go through. They're showing you an ATP molecule there, and they're saying, nope, you don't have to use ATP to power this thing. It's just like an open tunnel that anything can go through. Wherever there's a higher concentration, water will push through and go through it, and it's in the side of the cell. It's in the membrane. That's a great video, right? Shows you that water will go through, and water will go from water will go from higher concentration to lower concentration, which is what I'm showing you right now. Okay, so these are today's notes that we're working on. So I'm actually going to flip back to yesterday's notes, and I'm going to draw an aquaporin right here. Okay, so I'm just going to use the closest thing I've got to teal, because they use teal in their video. And I'm just going to draw a teal aquaporin right here. Okay, I'm going to label that aquaporin. And now I'm going to show an arrow going through and water coming in. Now, the cell membrane is normally impermeable to salt unless it wants to open special tunnels for salt. So, this cell can let water in and out, doesn't let salt through, and so if we put a cell into a solution that's 98 and the cell is 98, the water is not going to go more one direction than the other, so the cell is going to stay the same shape. But what happens if we have our cell? Actually, I'm not going to draw the cell yet, but let's say we drop our 98% cell into a solution that is 90% water and 10% salt. So it's a really salty solution. All right, here's a video of this idea.
Red blood cells must deform when they squeeze through small blood vessels. In this experiment, a red blood cell is pushed and deformed with laser tweezers. It quickly
Laser tweezers? I need some laser tweezers. I don't know how much those cost, but I need to get some.
What are you going to use it for?
springs back to its original shape because it has an extremely tough cytoskeleton to which the plasma membrane is anchored.
Do you hear that? So it's got a cytoskeleton inside of it that is pushing it out in every direction, so it's really springy.
When the cell is placed in high salt solution, however, the shape changes dramatically. Driven by the difference in osmotic pressure, water rushes out of the cell, causing spike-like protrusions to form as the cell collapses.
That's awesome. Turns into like a pine cone. So our happy little cell, if you put him in salt water, turns into an angry little cell that looks like a pine cone. Okay, so our cell is going to shrivel up because all of the water rushes out of him. So he's trying to get to 90%. And so I'm going to just draw an arrow of the water going out. And he's trying to get to 90% on the inside. And he's going to be an angry cell. There's his anger. All right, now our last option is, what if we put our cell in pure water that's like 100% water and has no salt? All right, here we go. We got some red blood cells under the microscope, and they are going to be put into what's called a hypertonic solution, which is distilled water, pure water, no salt in it whatsoever. This is even less salt than what comes out of the tap. And basically you boil water and then you collect the steam, and it's got nothing in it, no minerals whatsoever. And I don't know if you can tell, but these guys are gonna start growing at some point. Actually it says, there we go, there's distilled water. And so right about now, they're like, guys, I don't feel so good. Something doesn't feel right inside. Oh, the humanity. Imagine being one of these cells watching your friends explode. This last guy, he's like, that's not pretty. It's like a horror movie for red blood cells. So you look at the start. Oh, look how cute the little baby cells. And then you get to this point and it's like, oh my gosh, you guys, you gotta stop eating so much. And then blam, blam, blam. It's like when you ever seen these videos where the soccer players, you gotta see this. Okay, I don't know if you guys know, but maybe you can tell by now. I'm not a huge football fan. I love soccer.
My strength teaches my hands to war.
And soccer players will flop because they think they're more likely to get a foul. And, you know, it's just like mentally in their brain to stop running if they get touched by the ball. And sometimes it's just the most ridiculous moment. Right? That was a good one.
My shield, and he in whom I trust.
Oh! Too good. So anyway, sort of like cells blowing up in a hypertonic solution, right? Go on with the science.
You may proceed.
So if we take a cell that's 98% water, we put it in a solution that's 100% water, the cell will fill, but then it will eventually reach a maximum to where the cell membrane will burst open and water will come bursting out. Again, here's our normal red blood cell, put it into a solution of pure water, and it fills up with water until it explodes. We need to not forget to put a panic face on him and some eyeballs. All right, so animal cells, when you see this shape, think animal cells circle. And in pure water, animal cells explode, or burst is sometimes the word I use. And this is what animal cells do in salty water. They shrivel. And this is what gives a shriveled animal cell its spikes. Its spikes are from its cytoskeleton. All right, now, plant cells are a little different. Check this out. Osmosis in plant cells. Okay, again, we're going to use 98% water, 2% salt in your stereotypical plant cell. Now remember, plant cells tend to be square or rectangular, and they have a cell wall and a cell membrane. So if our happy little plant cell is going to stay the same, he's going to have water going in and out in the same way, he's going to be 98% water on the inside as well. So we'll assume that for all three of these scenarios. Okay, first off, we'll go with plants in soil. salt water, 90% water, 10% salt. I know what you're thinking. Johnny, how do you draw such exquisite plant cells? Hey, don't beat yourself up. It takes years of practice.
Don't forget, I'm a prodigy.
All right, homeboy does a little plant surgery. Ka-chow. Puts a slice of a plant on a slide under a cover slip and puts it under the microscope. And actually, this is the coolest part. You can drip salt water under that cover slip while you have it under the microscope. So you can literally watch what happens. It's called wicking. It's a technique where you just wick the water under the cover slip after it's already there. Well, wicking is pretty wicked. Oh man, the dad jokes are strong. So what happens when you add salt water through a wicked method? Look at this. The cell membrane pulls away from the cell wall and makes a round, I can't say any more words that start with a W, makes a round cell. And so you can see the plasma membrane separate from the cell wall. Okay, so I'm gonna outline the cell wall in brown. That's not brown. That is so not brown, man. Okay, so I'm gonna outline the cell wall in brown. See how that's the cell wall right there? That's brown. And then I'm going to outline the cell membrane in blue. And so this is the cell membrane. So there's like this empty space between the cell membrane and the cell wall. I wonder what's in that empty space. Okay, and so that is how the plant cell do. So if you put a plant cell into salty water, his cell wall stays the same, but his cell membrane shrivels. It turns into a little ball like that. Okay, and we're gonna go with, well, let's make this green, okay, because he's a green little plant in there, but now he's just like, let's get some brown. Got the blue salt water everywhere else. All right, last one. What if we go pure water, no salt? Is he gonna explode like this, homeboy? Oh, and this guy, is he gonna be, I'm gonna say he's grumpy. All right, so now same video. It was actually at the start they did hypotonic solution, which is pure water. And so here we go, we're gonna watch pure water, and he just gets bulgy. Look what it says. Distilled water is hypotonic, which means pure water, so it makes the cells gain water and swell. The rigid cells prevent the cells from bursting. So you can't really tell the difference, I feel like, from isotonic, so pure or regular water, to hypotonic, pure water, but the cells get bulgy, okay? Now let me show you what this really kind of looks like. Okay, so here's a plant who loses all of its water. So I think we've all seen this as kids. The plants, when it dries out, the plants, their leaves get floppy and they kind of fall over, you know? Like if you don't water a plant, it slowly dries out and dies, okay? This guy watered his plant, and filmed it in time lapse, and look at that. Isn't that amazing how a plant can return? Let's just watch that one more time. This plant returns to like a healthy state because its cells all fill up. Now think about that in terms of its cells. Every cell fills with water, and this is called osmotic pressure. Plants don't have a skeleton, they have osmotic pressure. All their cells fill with water, and they regain pressure, and all that pressure together fill up the plant with pressure, and the plant, it gets back all of his pressure to put up his leaves and regain the ability to stick himself out there to absorb sunlight. And so this is really the situation a plant wants. He's like a square, but he's like a bulging square. So he's a square, but he's got like bulging edges, and he's bulging out. His cell wall is keeping him from exploding, and he's just out there bulging out, filled with tons of water. Remember that central vacuole? We got to go way back to lesson 2, lesson on plants, but they have this thing called the central vacuole that's just for holding water. And so they will store lots and lots of water in here and still have the right amount of salt everywhere else. And they'll store tons of water in that central vacuole for the times when they've got plenty of water around. And so you got a bulging plant cell here, and lots of pure water on the outside. This guy's gonna be like, whoa, I've got so much water. Okay, now I just realized that I stopped drawing arrows of which direction the water was going here. But in this guy, the water is going in. In this guy, it's equal. In this guy, the water's coming out. And in this guy, the water's going in. So let's go back to plants here. When you see this shape, think plant cell, square. Okay, this is what happens to plant cells in pure water. They bulge. This is what happens to plant cells in salty water. They shrivel in a square. So they keep their square, but then they shrivel. And these are the two things you see when a plant cell shrivels. You see a circle and a square. All right, this brings us back to the big question. How does the truth that cells become filled with whatever they are close to relate to our spiritual lives? Okay, I'm going to read a few verses from the Bible to you. Walk with the wise and become wise. Associate with fools and get in trouble. Bad company corrupts good character. Don't befriend angry people or you will learn to be like them. Your eyes are the lamp of your body. So what we saw today is that cells will be affected by what they're around. If a cell is in salty water, all the water that's in the cell will get sucked out into the salty environment because the cell has a higher concentration of water, and diffusion happens high concentration to low concentration. And so if the cell has a higher concentration of water, the water will come out to try to go balance out the low concentration outside. If there's a higher concentration of water outside the cell, the water will come into the cell to try to make the cell have a higher concentration of water. It's kind of the same with humans, I think. Whatever we put ourselves around, we will become more like that thing. That last verse I read was Jesus. Your eyes are the lamp of your body. In a sense, when you read that in context and you read what wise pastors and theologians have said about that verse, Jesus is basically saying, like today a better metaphor than a lamp, because like we don't use lamps as much, would be your eyes are the window of your soul. Like kind of like, what do you let in to your soul through your eyes, you know? And I don't have my phone here today, but what do you let in through your phone into your eyes? Or what do you let in through screens into your eyes? Or what do you let in through the people around you into your soul? And then those other proverbs, if you let angry people around you, you're going to learn to be angry. If you let bad company, you know, like if you let people around you who are bad influences, they're going to influence you. But if you hang out with the wise, you'll become wise. And so in the same way that cells will be affected by what's around them, we as humans, whoever we choose to befriend, we will become like our friends. Whoever are your closest friends, those are the people you're going to become like. And so choose your friends wisely. Another proverb, guard your heart, guard your soul. Control what's coming through those windows because it controls the course of your life. It determines the course of your life. Very important, not just to learn science, but sometimes what my big questions are about is about the spiritual health of your life. So guard your life. Guard who's around you. Make wise decisions, for it determines the course of who you will become. Hope this is a great lesson for you. Peace out, Girl Scouts.